Dear grade 9 students, welcome back to the chapter circles. In this period, we will focus on few more theorems related to chords of circles. Let's see the first theorem. Equal chords of a circle are equidistant from the center. So given condition is equal chords. So let's consider two chords equal. You can have more than two chords of equal measurement. So we have two chords of equal measurement. Then the theorem says that the distance from the center are equal. So if this is x centimeters, this will also be x centimeters. Once again, the theorem says if the chords are equal, then the distance from the center are equal. But remember, distance means it should be 90 degree, perpendicular height. Let's see the next theorem. It is the converse of the current theorem, which means if the distance from the center are equal, then the chords are equal. Again, the angle should be 90 degree. So in general, the theorem says if the chords are equal, then the distance from the center are equal, and the converse is also true. Let us see an example here. If two intersecting chords of a circle makes equal angle with the diameter passing through their point of intersection. Equal angle through the diameter of the point of intersection. Let this be the diameter. And the chords, let's say AB and PQ. The angles are equal. Now we have to show that the chords are equal. So to prove AB is equal to PQ. For that, let's construct perpendiculars from the center O. So let O be the center. And OK perpendicular to PQ. And one more construction, OL perpendicular to AB. These are the constructions. Great. Now our target is to show that the chords are equal. And we have studied the theorem, if the distance from the center are equal, then the chords are equal. So we are going to prove that OK is equal to OL. For that, we have 90 degrees in both this triangle. We have equal angles and a common side. So in triangle, OK, we need a letter here, X. OKX. And triangle OLX. Angle KXO is equal to angle LXO given. Angle K and L are 90 degree because they are perpendiculars. And we have XO is common. So are we going to apply RHS theorem or AAS theorem? We have a right angle, but we don't have anything about the second side. We have the hypotenuse, but not about the second side. So RHS will not work here. So it is angle side by AAS. Triangle KXO is congruent to triangle LXO. So by CPCT, we can find that KO is equal to LO, corresponding parts of congruent triangle. Therefore, AB, the chord AB is equal to chord PQ because chords equidistant from the center are equal. That was to be proved and we did it. Moving on to the exercise, question 1. Two circles of radii 5 cm and 3 cm intersect at 2 points. So we have a circle of 5 cm radius and another circle of radius 3 cm. Let's write it here, 3 cm. And why the center is taken inside? Because the distance between the centers is 4 centimeter. The distance from the center of the large circle to the boundary of the circle is 5. The distance between the centers is 4, which means the center of the second circle should be inside. And we have to consider a common chord. Let's call it AB. The distance between them is 4 centimeters. The question here is to find the length of AB. This is the question. For that, we need a construction. Let's continue or extend the line connecting the centers. Let P be one of the center and Q be the second center. So let us extend PQ to R. Why did we extend here? Because we have studied a theorem connecting the centers of two circles. The line joining the centers of the circle is perpendicular bisector of the common chord. So we can find that the angle here is 90 degree and the chord is bisected. So we can find, let's name it T. AT is equal to TB and angle ATQ is 90 degree because line joining centers of two circles is a perpendicular bisector of the common chord. It is simple, just it meets at the midpoint and the angle that meets is 90 degrees. That's what we have observed in this theorem. Now let's name AT is X. So let AT is equal to X. So AB will be 2 times X. So we have to find out X. For that, in triangle ATQ, we know that is a right triangle because the angle here is 90 degree. AT square plus TQ square is equal to 3 square. I will draw the triangle here. It's like that. Here we have X and this is 3 centimeters. This distance from Q to T we don't know. Let's mark it Y centimeters. So this distance is Y. So we can find X square plus Y square is equal to 3 square by Pythagoras theorem. Or we can simply say that X square, because our target is to find X. X square is equal to 9 minus Y square. So this is an equation that we will use to find the value of X. Again, in triangle ATP, we can find X square plus the second side is 4 and Y together. So 4 plus Y, the whole is equal to 5 square. I will draw the large triangle here. It's like this. The radius is 5 centimeter. This is 4, this is Y. So the base will be 4 plus Y together. And the height is X. So let's expand it by the property A plus B the whole square, or the identity A plus B whole square. So X square plus 4 square is 16 plus 2 times 4 times Y, which is 8Y plus Y square is equal to 25. But we know that X square is 9 minus Y square. So we are going to replace 9 minus Y square. This is from X square. Plus 16 plus 8Y plus Y square is equal to 25. Y square and Y square get cancelled. 9 plus 16 is 25. When you move to the other side, it will be minus 25. So 25 minus 25 is 0, or Y is equal to 0. Y is equal to 0, which let us know that the point Q and T are the same. There is no distance between them, which means the point is C. So we can replace the value of Y in the equation. Let's name this as equation 1. from equation 1, x square plus 0 square is equal to 9, or x square is equal to 9, x is equal to 3. Therefore, AB is equal to, we need to get AB. This is x, this is x. So 2 times 3, which is 6 centimeters. Well, moving on to the next question. If two equal chords of a circle intersect within the circle, so we have two equal chords, let's name it AB and PQ, they are equal. Prove that the segments of one chord are equal to corresponding segments of the other chord, which means we have to show that TQ is equal to TB and AT is equal to PT. We are given that AB is equal to PQ. To prove this, we have to take a construction. Draw the perpendiculars from the center. Let M and N. Let OM is perpendicular to PQ and ON is perpendicular to AB. Since the chords are of equal measurement, then the distance will be the same. So OM is equal to ON by theorem. Equal chords are equidistant from the center. So OM is equal to ON. And there is a 90 degree. OT is common. So we have angle M is equal to angle N is 90 degree because it is the distance. So we have right angle and we have a side here. Now, what about OT? OT is common. And it is the hypotenuse. So by RHS, triangle MTO is congruent to NTO. So we found out that MT is equal to TN by corresponding parts of congruent triangles. So we found these two parts are equal. Let this be equation number 1. And we know that MQ is half of PQ because perpendiculars from the center bisect the chord. And half of PQ is the same as half of AB because AB and PQ are the same. And half of AB means it is NB. And let this be equation number 2. From 1 and 2, or when you add 1 and 2, we will get MT plus MQ. MT plus MQ is equal to NT plus NB. MT plus MQ is TQ. Therefore, TQ is equal to Tn plus Nb is Tb. So we found one part of the proof. Next, we have to show AT and PT are the same. Let this be equation 3. We already know that PQ is equal to AB. Let this be equation 4. Now 4 minus equation 3 will give us PQ minus TQ. PQ minus TQ is PT is equal to AB minus TB is AT. That was the second proof. Moving on to question 3. If two equal chords of a circle intersect within the circle. Proof that the line joining the point of intersection to the center makes equal angles with the chord. We have to show that these two angles are same. This is to be shown. But given condition, chords are equal. Chord AB is equal to chord PQ. So let's construct perpendiculars. OB the center, M and T are perpendiculars. So let OM perpendicular to PQ and OT perpendicular to AB. To prove angle MRO is equal to angle TRO. So let's take the triangles. In triangle OMR and triangle OTR, we can find that OR is common. Angle M is equal to angle T is 90 degrees because they are the perpendicular, or they are the distances from the center. Because the chords are equal, OM is equal to OT. Equal chords are equidistant from the center. So we have a right angle, hypotenuse, and a side. So by RHS, these two triangles are congruent. OMR is congruent to triangle OTR. So by CPCT, we can see that angle MRO, therefore, angle MRO is equal to angle TRO. Corresponding parts of congruent triangles. That was to be proved. Moving on to question 4. If a line intersects two concentric circles, concentric circle means two or more circles that have same center. With circle O at ABCD. So the line is meeting or intersecting two circles at the point A, B, C, and D. We have to prove that AB is equal to CD. For that, let us again do a construction. Draw a perpendicular from O to P. Let OP be perpendicular to the line AD. It is a construction. Now, for the small circle, BC is a chord and it is bisected because it is a perpendicular. BP is equal to PC because perpendiculars from the center bisect the chord. Also, AP is equal to PD, the same reason in the large circle. Let's name this as equation 1 and this is equation 2. Equation 2 minus 1, which means AP minus BP is equal to PD minus PC. Now we have to take it from the figure. AP minus BP, which means this part, which is AB, is equal to PD minus PC, which is this part, CD. That is what we have to prove. Now, question 5 can be done in 2 different ways. So we will see it in the next period. That's all for today. Thanks for watching.